Okay, let's get started. Welcome to lecture 6 of the coding period. So, the topic today of discussion is actually one of my personal favorites. I was introduced to this about 2.5 decades ago. To this day, it sort of dazzles me with its brilliance, elegance, and simplicity. One might argue that it's unmatched in its records. It's been equaled by other codes and their records and sort of unmatched. And some might even argue that it's been surpassed by others in its performance. But in my eyes, it's unrivaled and it's definitely the code. To be mistaken that I'm talking about the Roger Federer. I possibly should, but we'll be talking about the Reed-Solomon code. Just as remarkable, just as fantastic. Thanks, Roger, for all the tennis. Yeah. Let's get to Reed-Solomon codes. What are Reed-Solomon codes? And in Roger's case, there's always an underlying field, a finite field in this case. So think of F as some finite field. We'll come, so I'll first define the object. We'll talk about what the Reed-Solomon codes are, and then we'll go to some operations with finite fields. The finite fields, assuming most of you have done it in the math structures course, we are always of this size. So the size of F we'll assume is some cube. This will always be a prime power. So finite fields only happen in prime powers. We'll talk about these things. We'll actually, at the end of the lecture, we'll actually talk about, we just don't need finite fields, we also need how to work with finite fields. We need to do computations with them and see how to go about it. But for now, we have a finite field, so it's a cardinality Q. And the Reed-Solomon code doesn't refer to a single code, it actually refers to a whole family of codes. And it's parameterized, the family is parameterized by 3 quantities. One is the finite field, F. Next is S, which is what we call a set of evaluation points. We say the size of S is n, and K, the degree parameter. Actually, one more than the degree, and you'll see why that's the case. So, and these 3 parameters will satisfy the following relationships. That is, Q will we'll be defining it as Q is larger than N, is larger than K, and it is at least 1. So that's for any choice of finite field, set of evaluation points, and K, we will define the Reed-Solomon code. So what is the Reed-Solomon code? First, we will talk about the underlying alphabet. The alphabet will be the field itself. That will be the underlying alphabet of the code. And what is the code? So the code, we describe it. The code is usually described as by giving you the set of code words. So we'll have one code word. So let P be a degree less than K polynomial. With coefficients coming from F. In short, the P of X belongs to what I call, it's a ring of polynomials Fx, but its degree is less than 2. Strictly less than 2. That's what the shorthand notation I will use for this. Take P to be this. And then, one more feature, that is this S is not just a set, there is an ordering among the elements. ordered set. So that's an alpha 1, then an alpha 2. So it's a tuple rather than just a set. So the element, which we know the first element of F, the second element of S, and so on. Notice these are all distinct elements in the finite field. Because we're choosing to do this. What is the code word? This is the code word. Just evaluate this polynomial at the points. This belongs to what we call the Solomon again. Yes, okay. There's no standard, no. I don't think there's standard definition of putting this up for this lecture, but there are various ways of writing this. Okay, you follow what the Solomon is. For every polynomial P that you take this way, write down its evaluation vector on the list of points, and that is a member of the Solomon. So, how many such code words are there? We have just as many as there are polynomials. How many polynomials are there? Q power k. Q power k, because you can. This is why I'm choosing less than k, because then there are exactly k possible coefficients. You can take the 0th coefficient all the way up to the k minus first coefficient. There also p is the p of x can be determined to be equal to whatever. You can think of it as summation I, x power I going from 0 to k minus 1. And therefore, you can think of the Solomon code as sort of this particular Solomon code as mapping f to the k to f to the k. That's what it's taking the polynomial p and mapping it to its evaluation to p alpha. Okay. Notice it's also, I give you a different choice of S, a different choice of P, it's a different mapping out there. But for each K and each S, there is that underlying object is called the Solomon code. And usually standard to consider two settings of S. One is S is the entire field itself. S is the whole field. The other is S is just a multiplicative group of the field. That is, you drop the field. So it is just F minus the non-zero location of this one. And you'll see, we'll later on see why it's nice to work with. Sometimes it's nice to work with these things. But almost everything we do in this course will work with any choice of S. So historically, I think the definition of Reed-Solomon referred to this F star, and everything else was called the generalized Reed-Solomon code or sort of this one, but we'll not use that notation. We'll use Reed-Solomon code for any S. So usually when you specify Reed-Solomon code, you have to specify the set of evaluation points. It will be implicit, but you have to specify it. So we'll assume it is some set yes, and our algorithm, everything will work for an arbitrary set yes. We'll try. If it doesn't, we will explicitly say. Yeah. So, each code corresponds to. We need to do one check. We need to do that's one sanity check. We need to do that. No two polynomials map to the that this is a 1-1 mapping. We'll do all of that right now. Okay. So I haven't. So in that sense, I didn't fully answer Sridhar's question. That is whether this is the. Certainly, it's a mapping from every polynomial. There's one guy here, but I haven't told that the rate of the code is t. At least the rate of the code, the dimension of the code is t. For that, I need to show it's 1-1. Otherwise, two things are collapsing picture.
What is relative?
Huh?
What is relative?
I need. Yeah, no, n is greater than or equal to k, no?
Oh, n is greater.
Yeah, n is greater than or equal to k. Yeah. Okay, we will answer that shortly. So we will tell what sort of code it is, but I want to make a few more observations before we go to before we actually go into what the results are very important. We will do a bunch of observations, one of which will be that. So something may. The first one will be RS F SK. It's a linear code, F linear code. Why is, you'll see that, why is this true? What does it mean by linear code? Yeah, so if you take two polynomials, if you add them up, you should get another polynomial, certainly you do, to the degree. And you should also be able to scale a polynomial. You multiply a polynomial with a scalar from the field, you remain in the set of. And this is just all of people. Polynomial in x less than k, x closed under addition and so it's a nice linear code. The next property, which will answer this question as well as even stronger property, what we show is RS SK meets Hamilton point. That is D plus D. Yeah, that is D plus K equals N plus 1, where D is that is the distance, in fact, equality N minus K. Show that it matches the symmetry one. And particularly the distances is where it has two things have to be what I'll show you gave me more precisely to show the following. So the following name. If PQ or less than KX and P not equal to Q, that is there is some coefficient with one, then the number of alpha in S such that P alpha is equal to Q alpha with the utmost this and the distance property will be an immediate corollary of this because that means they at least disagree on n minus k plus 1 points. Therefore, that's the distance is at least greater than that. Singleton bound tells you it can't be greater than that, you have to be equal. The distance will be equal. And this plane itself will be proved by a further plane, which we will be using repeatedly all over again for the degree mantra. See if we can prove this also later on, but for now we'll again. So basically, if you take the degree R polynomial, it can have at most R roots. If you take a degree R polynomial over a field, this is important. This is where the field is variable. It's not true over the field. So P belongs to F less than equal to R X and P is not 0, then P has at most R roots. And R roots not just in yes or anything, R roots period. Anywhere in the field, yeah, in the field extension, anywhere, this is the number of roots that P can have. This is something we will use over and over again. And the same, you have seen the proof of this previous somewhere on. If not, we'll do anyway, we'll do the proof of this.
Very basic question. Every finite field is algebraic close?
No, finite fields are not arbitrary. So
Then an extent.
they will always have it. For example, the finite field, what the relate is of course, if you recall fact, basic fact about finite field, take the finite field, things model of P. You know x bar P minus x. Everything is a solution of that. In general, for any finite field of size q, x bar q minus x is the polynomial so that every element of the finite field is a responder. So certainly, you take the polynomial x bar q minus x plus 1. It has no root in this finite field. You have to add an extension. You have to go to an extension field to add it. And in fact, if you do finite field, there is no finite field which will be algebraically closed, but there is an infinite extension which which it's closed. You just keep on adjoining and do that.
So for this to work, we will always work in a large enough field. And
What do you mean this to work?
I mean,
This I'm claiming is just a R root. This will not perform here. And I'm claiming this R root is not just in this, particularly it's also true in this field. Take it to your slightly large extension field, it still will be true. Take it to any field, it will be true. You can never, you can always adjoin enough roots that the polynomial completely factorizes. And even at that point, claiming it will never have more than one. You could be in a field setting where it has no roots. So that's why ideally I should specify in F, but I'm going to keep that sort of one. And this immediately implies the proof of previous claim by just working with P minus Q. So that's for the previous one, just work with the polynomial P minus Q. Because P is not equal to Q, that's a non-zero polynomial. Hence, it can have at most K minus 1 roots and things. Those are exactly the places identical. So these are in anywhere, in particular, even in S, they can have at most K minus. Question? So this will actually tell you that two polynomials it's not just a 1-1 mapping, actually it's a mapping in which they are very, very different. You take two distinct polynomials, if you map them, if you follow this mapping, we follow mapping over here. Underline something. So this is not just, it's not onto, but it's certainly 1-1. No, it's not just 1-1. Two different P and Q are different. The corresponding evaluation vectors will look very, very different. They are going to disagree in at least n minus k plus 1 points. So to put that all short, what I'm stating is the following: RS what we've seen so far in short. RS yes, so let's write it in the coding notation. So I want to put in the 3, 4. With the linear code, those are the square brackets. The alphabet size is Q. The dimension is, the ambient dimension, the ambient space is N. The dimension of the code is K. That's why I chose K and the degree to be 1 above the right degree rather than this. And then minus 2. By the way, so recall we showed that the distance is at least n minus k plus 1. Singleton bound will tell you that the distance is actually n minus k plus 1. It can't be any more than that. But that means you must also show me two code words which have exactly that distance. What's an example of two code words that have exactly that distance?
Any k point c minus 1.6 is and a product x minus ai that subset.
Yeah.
That's distance from 0 is minus k plus 1.
Yeah, so take any k minus 1 point in the fifth one, take the product there, take the product of x minus the a for a in that set. So this will be a polynomial which has k minus 1 roots. You can't have any more roots, but if it had one more root, the degree will have to be larger. So its distance from 0 is exactly n minus k plus 1. So that's an example where it's not just the example of forward. So it's not just this one. In fact, you can take any two, take this and add it to any polynomial. So that polynomial plus this will also have the same. That's the main takeaway at the end of this. So it is. So in that sense, it's an amazing code. It matches the singleton code. Very few codes for which we have this family of codes. The main caveat with some code is Q. The fact is, unlike any other code which we have seen so far, all the codes which we have seen, we work with a fixed finite alphabet, fixed size alphabet. The alphabet was either Boolean, some 3, 4, or something. Here, the notice the alphabet is growing with this one. So Q has to be larger than n to even make sense. I need to choose n distinct points as evaluation. And so the n should be smaller than Q. Therefore, even define the code as alphabet has to be at least linear in the dimension of the. So this is the issue with the recurrent code. But of course, we saw previously that you can't have codes over a fixed alphabet that will meet the same number. The plot pin bond which is spanning period, and you need to get around this. That's why we are having codes which are going to have alphabet sizes which grow with n. And an example, as an amazing example, we will see almost all code constructions that we will see, most of them, over cell will start from Reed Solomon and will eventually come to codes over a smaller alphabet. Any questions on the Reed Solomon code? So what we'll do next? Yeah. So what we'll do next is there's a linear code. So now, in particular, if it's a linear code, it has to have nice representations. What are the representations we're talking about when we have linear codes? Parity check and the generator matrix. So let's see if we can come up with nice generator matrix and parity check matrix representations for this code. Generator matrix, I want to say, is already sort of implicitly. Notice there's no one choice of generator matrix. I told you, you just pick any basis for the linear space, and that will be a generator matrix. Similarly, parity check matrix is any basis for the dual space. If you get that, will be a parity check matrix. But what we will see is actually there are very nice bases. This code, as we'll see over the course, it has the extremely nice property. So what, and I also want to say that we actually already seen, I'm not expressing it explicitly, but implicitly we have seen a generator matrix view of this code. So what is it doing? What's a generator matrix? It's taking a message and it has to input and it has to output the code word. We already saw it takes the polynomial p and then outputs the evaluation. What was that? It was this with respect to. Let's take the generator matrix point of view. Generator matrix. It's a generator matrix. Or we solve them. What did we see? We saw that we had P of X, which was summation P I per I, I'm going from 0 to k minus 1 was getting mapped to p alpha 1, p alpha, alpha index. We're very excited about the map. What this map getting? It's basically looking at this vector p0, p1, all the way up to pk minus 1. And it's multiplying with 1, alpha 1 squared, all the way up to alpha 1 to the k minus 1. We multiply this, we do that multiplication, what you actually get is p of alpha. P of alpha 1.
E0.
No, p of alpha. P is this, the coefficient vector, so you get p of alpha. And similarly, this is 1 alpha 2. 2k minus 1, you get p of alpha. And this is 1 alpha n. Yeah, so that is already when we already talked about it as an evaluation. We already had this generator matrix point of view, and it's a very nice generator. Typically, when we talk about Reed-Solomon, we'll always refer to this as the generating matrix. And what are the generating matrices? So there are two ways multiple ways to look at it. One is this side, so let's look at this matrix. On this side, it's indexed by points in S. On the other side, it's indexed by all monomials. So for every monomial, so columns, this is up to the choice. Then we go for the monomial, the empty monomial, the degree 1 monomial, the degree 2 monomial, all the way up to degree k minus 1. And this is basically the one. Most places you will see it, the transpose of it, because they work with the code words, the row vectors rather than column vectors. S will be on the rows and the monomials will be on the columns. The other way around. I also get the rows and columns in this. But if you follow what I mean. So it's got a super nice one. And let's also try to do the parity check. Parity check will take us a while to come to. Parity check viewpoint, because we need to understand the dual of the Reed-Solomon code. We'll defer that to a little later. But I want to talk about some more properties just with this viewpoint of. So by the way, so what did we see? We saw that the Reed-Solomon code matches the singleton code. It's one of those rare codes which achieves the singleton form. By the way, so it's not the only code that achieves the singleton form. There are others that are equal in effort. It's you will see something in your problems that I'll give you examples. The other, but also polynomial based code, all of which will match the singleton mode. They all have distance equals and not scales.
Random codes over large alphabets matches.
It's a random code. So singleton bond is something you have to match in its precision. It's not something like it's not a bound in which you have to be greater than you have to match it exactly. And you'll see this the next property which I'm going to talk about with the singleton code that matches singleton bond. It's an amazing property, and it's very difficult for a random code to have. So any code that matches singleton bond, you just see it's what's going to be called to do. It's going to call what we call maximum, either you might have heard this name, distance separable codes. MDS code. What is an MDS code? MDS code is just a code that meets this, that achieves the singleton form. That's the definition. And why do I call this? So in a code is said to be MDS. If it achieves the singleton form. And so far, we have seen one example of a code, Reed-Solomon code. There are other codes. Most likely the problem set will have, the second problem set will have examples of non-Reed-Solomon, but still polynomial-based MDS codes. What I want to say about this MDS code is then, or any code that's MDS has some amazing properties. What's the property I want to highlight for? P D Q code MDS code. Yeah. So C is such a code. I want to say take any what is n is the set of coordinates. Now let's take any set T. Then for all T subsets of n, where the size of T is K. So take an arbitrary subset points. In the case of Reed-Solomon, what does this mean? This I'm choosing some subsets of the evaluation point. Evaluation point for n. I'm choosing a subset P which is smaller than n. And let's look at the restriction of the code just as this. Let us knock off the projection elsewhere. I want to claim this will be now it will become a projection. So notice what I want to say. Then for all T, the size of C restricted to T is exactly Q to the power 2. And what is C restricted to T? Where what is C restricted to T? C restricted to T is just C restricted to T, where C belongs to C. And what does C restricted to T mean? It's the obvious thing that C restricted to T is take the code word on n coordinates, drop, just knock off every coordinate outside this. Take the smaller. That's the one. So just take the restriction of the code to these P coordinates. And this could be any P coordinate. I want to claim this restriction does not, you don't lose any information. The whole code is out there. Let's look at this for the Reed-Solomon code. What does it say? You give me the evaluation at A points. That's enough to recover the polynomial. You can interpolate. If you give me the evaluation of the polynomial at A distinct points, it's important that the K distinct point, that way we need P to be K. In nothing smaller is suffice. You give me the evaluation at K points, any K points, that's enough to recover the polynomial. In other words, you just look at the smaller K by K matrix. Sorry, is it a K by K? Yeah, it's a K by K matrix. That's enough. In fact, just take just this K value, the evaluation of the polynomial of these K. That's, if you know that they were correct, that's enough to completely recover the polynomial. And hence that's why CPK is this one. Every polynomial continues, there is no two polynomials collapse the same. They can project to this. That's what this theorem is stating. And I want to claim this is not just a property of Reed-Solomon. Reed-Solomon is evident in the fact we just come from what we call the interpolation. Take any K distinct points, there exists a unique polynomial of degree at most K minus 1 that passes through these K points. Of interpolation. By the way, the interpolation, why is that true? Why is that statement true? Why is there a unique polynomial? But why is another one? It's unique because otherwise. It's because you're looking at the van der Waals matrix. You're looking at, so this van der Waals matrix. This is, by the way, this is called van der Waals matrix. And why? Let's see the proof of this for the. Let's see the proof of this in general also. But to start off with, let's see the proof for the Reed-Solomon case. Then so first for RS source. So without loss of generality, let's assume T is alpha 1 to alpha 3. Now, when you have the, you don't have the entire van der Waals matrix with you. You have just, you don't have all the rows of this. You have only the T rows corresponding to this one, and you're looking at that K by K. So you have a K by K matrix, multiplied with this, and you have this evaluation point. You want to know, is this invertible? Can you, from this set of things, can you go over here? So basically what we have right here is asking this question. We have the monomials over here. We have just T over here. And what we have here, we have alpha power I. That's the, for if this is for the alpha element and the I monomial, we have alpha for I. And this is a K by, now it's a K by K matrix, not an N by K matrix. And we are asking, and what we have here is just P of alpha 1 all the way up to P of alpha. We know we have only the evaluation at the points in T. We don't have all of them. You're basically asking, from this can I go to this? And you can do it only if this matrix is invertible. And we know the K by K van der Waals matrix is invertible. It's exactly the determinant of it is alpha I minus alpha j, where product of alpha I minus alpha j after signs. Yeah. We have to write them properly to define it well. Yeah. So because of that, this matrix is always invertible in the range. So please, in the Reed-Solomon case, so what does it tell you? You have a Reed-Solomon code word. You know K bits of information are sufficient to define the code. That's true for any code, any NKD code. That's what K means over there. Here I'm saying any K bits. So you pick up any K coordinates, that is enough to define the code. This is not true for other codes which we have seen so far. Not all K bits, K code word symbols will extend to one. True for the Reed-Solomon. Reed-Solomon, any K code word symbols are sufficient to actually extract the full code word you need.
So user is around code uniform and
Yeah,
distribution of the coordinates is K-wise given.
it's K wise independent. It is K minus. It's K wise independent. It's K wise
In the
independent.
assignment, the problem is the K-wise independent distribution must have support that list.
Yeah.
Does
So-
this give
So it will give you over, but not over the assignment wants it over the Boolean alphabet. So that's this one. So assignment will go harder because it's Boolean alphabet. For the large alphabet, yeah, read from that is you. Okay, so and this K by K random amount is invertible. Hence. Okay, that's fine. Okay, that's for Reed-Solomon. I want to be not just true for Reed-Solomon, it's true for any. Why is this true for anything? For any MBS code.
analyze the equal
Huh?
analyze qualification?
So let's take this exactly. Let's take so you look restricting view to K locations. Suppose two different code words matched. So more principle is the general case. Okay. So T is some sort of P and KT. MDS, which means that D is actually equal to N minus K plus 1. And T is some of 1. So suppose it were the case. So when is the theorem false? Suppose there exists C1 and C2 in the code, such that C1 when I restrict it to T is equal to C2 when I restrict it. So when I restrict to these T coordinates. Now, then what's the distance between C1 and C2?
At most, n minus one.
Then delta C1, C2. All the distance should come from the remaining coordinates. And the remaining coordinates is how much? It's n minus k. So it says the distance is n. You have two code words, but the distance is n minus k. But that contradicts the singleton bond. It's MDS, you know the code has to be n minus k plus 1. Therefore, this cannot happen. Because the contradiction. Hence, any two distinct code words, if you just look at the restriction to k location, they actually are very different. This is not just a property of the Reed-Solomon code, it's a property of every MBS. And actually, it's quite an amazing property. It basically says it's a property we take for granted with respect to polynomials. It says if you know the polynomial location in k points, then you can interpolate. So this is the amazing thing what can be.
So we for like the photo group, we don't have that means singleton bound. We don't need it with the code.
We don't need the
That the code is linear.
we don't need the code is linear.
Okay.
Change these brackets to this proofed with linear.
So given an MDS code, you have the normal code, or it's in terms of
No? You certainly can get, so you can show that the alphabet size has to be, you can show the alphabet has to be n.
and I got
In fact, I think you can get n. And so there are of course things which are larger, but I think you can get n, because it's not hard to see. It requires a bit of work, but it's not. Yeah. Basically, what are we asking? We are asking the following. So another equivalent way to treat the question is, so suppose we have a code which is MDS. So look at the generator matrix of this code. What are we stating? We are stating that the generator matrix is an n cross k. N cross k, yeah, it's an n cross k thing. We're stating that every k cross k submatrix is full rank, have rank k. We want this property of if and only if every k, if you have an n by k thing, so that every k by k is full rank, that means you can recover. So now ask, where should the symbols be coming from? The symbols have to come, you show that the alphabet is any smaller than n, actually this can't be the case. You will actually get the matrix. There will be one k by k matrix, submatrix, which is actually not the single. What will you do next? So I still haven't yet shown you the parity check viewpoint, because that will take some more effort. So what we will do for that is actually let's do some basic, let's recall some basic facts about finite fields. Most of it you would know, but I'm just going to state them because we will be using them both as facts about finite fields, and also we need these facts. We are not just going to need facts about finite fields, we actually need algorithms of finite fields later on in the course. In fact, in the very next lecture, we will ask, now that the Reed-Solomon code has this distance, can you uniquely decode from this distance? That will be our discussion. So the first algorithm tool will be actually trying to decode. We will need to operate with finite. So let's do a primer on finite fields. I go quite fast on this. I'm assuming most of you know. Okay, but this is just for that. So what are finite fields? So certainly there's FP, which are the prime fields. Those are finite fields. So these are just of the form 0, 1, 2, 3 up to 3 minus 1. And this is just regular integer addition, but everything happening in mod p. Integer addition, integer multiplication, and you know that this is a finite field. Okay, what's a field? One is a field, it has two operations in it. One is the addition operation. Under the addition operation, it should be a group. It should have commutativity, it should have an identity, it should have inverses. Similarly, multiplication, it should have under the group, under the operation multiplication, it should be commutated. The non-zero elements in the group will form a group under multiplication. This is where F star is going to come to the picture. And what is non-zero? Zero is the additive identity, is what I'm going to call zero. And then the multiplicative identity is what we'll call one. And then, more importantly, how the two operations, multiplication should be distributed over addition. A into B plus C should be A, B plus C. So this is all that we want to be. Many a time we'll also talk about rings, which have all the properties except one, in which the multiplicative, not all elements have inverses. For example, F. F is the set of elements. This could be finite, infinite. A cube with two binary operations. One is plus, which we call addition. And what we want of it, we want commutativity, commutative, identity, the existence of identity, which we refer to as zero, and okay, we also need associativity. And inverses. And then the another operation called multiplication. And we want the same set of properties. But this is for multiplication for the non-zero elements. And A into 0 is equal to 0 into A into 0 for all A by the time functions. And finally, we want distribution. A into B plus C equal to AB plus C. That's B. And a ring is all the above except for multiplicative rings. And certain examples of fields FP, the prime fields. And for prime fields, we'll assume we have all operations. We know how to do addition, we know how to do multiplication, all of just regular integer addition, integer multiplication, except you do mod p. So then you can also do inverses. Why can you do inverses easily? Huh?
Basically, equals to 1.
Yeah, so take the GCD of, if you want to find the inverse of A, you know A and P have GCD 1, therefore you run Euclid's algorithm, so you get an AX plus BP equals 1. Now, when you go mod P, this just means AX equals 1 mod P, X is the inverse for so you. So the very fact that you know when we say inverses, we will actually be computing inverses, right? That means you are going to be invoking Euclid's algorithm every now and then, whenever you say you pick up the inverse. So even for prime fields, we are going to be invoking Euclid's algorithm. Now, if you work with larger fields, you would have seen that the only type of fields that have are only prime powers. Fields can have only prime powers, because I will not prove this fact. So Then there are into the form FQ, where Q is P power R, P is prime, R is a positive integer. And so there are some things. What we would actually need is not just the fact that we need a representation that we'll be actually working with this. And the easiest way, one of the things which you possibly have seen is that FQ is actually isomorphic to take FP. Look at the ring of polynomials FPX, the univariate ring of polynomials, and go mod E of X, where E is an irreducible polynomial of degree exactly R. Use all of the words over here, so let me tell you what these are. So, and it should have been any irreducible polynomial. This will always give you back the same finite field. It will be different representation, but they'll always be the same finite. There's only one finite field of size Q to the R. But why is this a useful thing to keep? Addition becomes very easy. Addition is just polynomial addition. You have two elements of this, you use them as polynomials and just add the polynomials. Multiplication is also the same thing. You use them as polynomials, multiply the polynomials, go mod. What about division? Once again, you take any polynomial here, you know that you know that, so you use some fact that polynomial and E of X don't have any common factors. Because if they had, E of X won't be irreducible. Therefore, A and E have GCD is 1. Once again, you can do Euclid's algorithm, assuming you can do Euclid's algorithm over fields or over polynomials also. You do that, and then you get similarly A, you exactly as it is in the prime field, you will get the inverse. So you can do all of the operators. The multiplicative inverse can also be obtained. Whenever okay, so let's we need a few more facts before I get. So we're going to be working with these rings. F of X is these are polynomial rings. The ring of polynomials. You clear what it means. Just set up all polynomials whose coefficients come from X. This is a ring. It has all the properties. It doesn't have multiplicative inverse, but it has all the properties. And what I want to say is the things that we know about so there's this notion of factorization. So if F in the case that F is the field, we have the nice thing about what's called factorization, which is factorization is just the fact that if you're giving a polynomial F, if it can be written as GH, this is the usual thing. You can factorize the polynomial into the thing. And reducibility, you say F is reducible. F of X is reducible if there exists GH such that degree of G, degree of H are both greater than 0 and less than degree of F, and you have F equals GH. You have a non-trivial factorization. Of course, there's always trivial factorization. You can always pull out a field element, and there's always trivial factorization. I don't want trivial factorization. This ensures it's not a trivial factorization. And if this is not the case, this is when I call the polynomial to be reducible. And is irreducible. So that's what an irreducible polynomial. Irreducible polynomial is one which cannot be factorized. By the way, these properties don't happen to be true not just for univariate polynomial rings, they actually happen to be true even for multivariate polynomial rings. That is, I adjoin, it's not just f of x, y. There also you can talk about factorization, you can talk about reducibility, irreducibility, and okay. And we come to that in the next lecture, because we talk about multivariate polynomials and both are rising from them. I wanted to mention one. So, and the nice fact out here is both the univariate polynomial rings and the multivariate polynomial rings are actually have a similar property which the integers have. That if you have, this is just a imitating fact, primes and composites over here. I'm lifting that definition to the ring. Integers have another nice thing with something called unique factorization. That is, take any number, you can factorize it into primes, and this factorization is unique. Up to ordering and of these defined factors, this you take a number, there's only one way to factor. And this happens to be true even for multivariate polynomial rings. That if you take any polynomial, you can keep breaking. If it's not irreducible, you can keep breaking it, keep breaking it, till all the parts are all irreducible. So you can always start with an f, you can break it down into f1, f2, fr. So that all the fi's are now irreducible. If it was not irreducible, you know that there is a gh. This one, break it, keep breaking it, doing this. But then, because there's no order in this way, you could have done it with breaking in a different way. Suppose we manage to do G1, G2, Gs, where the FIs or FI and GJs are all irreducible. Then the claim is then 1 R equals S. And furthermore, the F's and G's are just unique up to permutations and scalar multiplications. Then R equal to S, and there exists permutation phi going from R to S and alpha 1, alpha 2, alpha R. Alpha 1, alpha 2, alpha R. That product of alpha I is 1, and Fi is just alpha I times G by 1. So F's and G's are basically the same up to permutation, but for some scalar ones, and those scalars have to eventually multiply. This is what makes this short for the unique factorization domain UFD. This is true for not just univariate polynomial rings, this is also true for multivariate polynomials. Both univariate polynomial rings over fields, and multivariate polynomial rings over fields are UFDs. That way you can factorize them, and there's a unique way of factorization. But over integers, we not just factorization. There's a way to do. I give you a number. If I give you a number A and I give you a number B, you could divide A by B. Process called division. This is a property which is among the integers we had this. Integers we have the following nice property of for the division, which is given AB among the positive integers. This could be among even, let me just work with just positive integers. There exists Q and R, which are called the quotient and the remainder, such that A equals PQ plus R. These are also non-negative integers. So the important property that Q, that R, so R is a number between 0 and strictly less than B. That's the key property of division. That is, you divide A by B, get a quotient, and the remainder is a number which is lies somewhere between R and B. This was important. This we have seen the division algorithm. On to claim univariate polynomials also have a similar division algorithm. This is not true for this is one place where multivariate and univariate will differ from each other. Univariate polynomials will have this. We can assume this with the division algorithm. This is true only for univariate polynomials. What is correct? I'm going to give you the given A of x, B of x in the polynomial ring. Want to say there exists something called the quotient polynomial in the remainder polynomial, also in f of x, also polynomial such that A of x, this is a polynomial identity, is actually B of x times Q of x plus R of x, where there we said that R was somehow smaller than B, and the measure of smaller was in terms of size. Here, how R will be smaller than B will be, we'll say the degree of R will be strictly smaller than the degree of. We'll say that where 0 less than or equal to the degree of R is strictly smaller than the degree of this. And actually, this exists. You should have seen, this actually an algorithmic process. If I give you an A and B, you can actually do this fastly. You would have seen these division algorithms for the polynomials, and we'll invoke this again and again to later on at the course when handling this. Given the division algorithm, the statement, the degree mantra should now be actually. Let's see a quick proof of degree mantra. So what do I want to say? I want to say a polynomial of degree R is actually R roots. And that follows from the fact that what does it mean to be alpha is the root of P of x. This is true if only if P of alpha is 0. Now, the division algorithm will tell you that I can divide P of x by x minus alpha and get a quotient polynomial 1 plus something. And that something has to be of degree smaller than x minus alpha. So in particular, it has to be a constant. It can't even be a linear polynomial. There's a constant. What can that constant be? Yeah, good. So if P of alpha is a root, then it is one. Suppose P, yeah. So that this guy I want to say has to be just, in general, it has to be P of alpha. In general, it has to be P of alpha, because now you can substitute alpha, you can evaluate this at alpha, this vanishes away. So this has to be P of alpha. So because of the division algorithm, we have this. And now if you reinterpret the statement, this states that if P of x is a root, that means if alpha is a root of P of x, then P of x is equal to x minus alpha into Q of x. So you can peel out the first root. Now let's go for the second root. Now I want to say alpha 2 is a root. Alpha 2 is a root. You apply, it has to, you plug in alpha 2 over here, you will get the Q of alpha 2 has to be 0. You can induct on Q. In inductive Q. But somewhere along this place is where you're going to use. So where is the property of fields being used over here? There's one is division algorithm. Division algorithm might also be true for rings, I believe. I think we should be able to do it. Here is where we'll be using this one. That is, I'm assuming this is
It's not true for
it, which is not true. Division algorithm is not
say
it is not true for the release model. Not true for the no, where am I using the fact that? So I want to say one of the places out here, I said that when I plug in alpha 2, this product, so this is alpha 2 minus alpha 1 times Q of alpha 2. I need to argue that either this is 0 or this is 0. So I need it to be an integral domain. That's where I will be using. So Q of alpha 2. So I have to do the even the recursive or inductive argument. I have to say now Q of alpha, that if alpha is a root of P of x, we got this. Now, if beta is another root of P of x, I want to say beta is now also a root of Q of x. And there you will use integral domain. That's where the field property will come. So now Q will get, you peel off another and you keep peeling. So if you have R roots, you keep peeling one after another. And you cannot, this process will have to stop. Otherwise, the degree of P will be larger than 1. So basically, this is true. If alpha is the root of this, in this one. So if alpha 1 alpha, continuing. Alpha 1, alpha 2, alpha R, the roots. P of x will be product of x minus alpha 9 equal to 1 to R and Q of x. It must be the case that Q of x has to be constant. Otherwise, P of x has a larger P. Rather, the other way, it has more roots. We already had this formation. You have a degree R polynomial, which is looks like larger than degree R. Let's go back to SQ. What we did is, when I mentioned this in passing, all elements of SQ. Roots of the polynomial x square q minus x. In fact, x square q minus x completely splits into linear factors, and all its roots are exactly the elements of. This is a nice thing about working with finite fields. You have a polynomial, all of whose roots are exactly the element of the finite field. Now I want to. So you recall in the beginning of the lecture, I said, with Solomon, we would use usual set of evaluations, either the whole field or F star. And why is this? Why is that? Why are those two interesting settings? So let's look at the case. Let's actually look at the case when we're working with prime field. Let's see the prime field. So in this case, the field looks like 0, 1, 2, P minus 1. Notice what is this? This is 0. This 1 is actually 0 plus 1. 2 is actually 1 plus 1. And then this is P minus 1 is P minus 2 plus 1. So it's sort of a cycle. By addition by 1, it sort of lets you this cycle through the whole thing. And in fact, 0 is P minus 1 plus 1. Okay, what's so great about this? So suppose I take the, let's look at the case when the evaluation point is S. Evaluation point S is FP. And I use this particular order 0, 1, 2, 3 up to p minus 1. I use that order. Now I take the polynomial a in f less than a x, and I write down its evaluation a of 0, a of 1, a of p minus 1. So that's how Reed-Solomon code works. Now suppose I shift it by just cyclically shift it. What is that? Is that a Reed-Solomon code work? Why?
The polynomial p is p of x minus 1.
Yeah, so if I just like, that's because of that property. So this over prime fields, when you take the evaluation point to be yes. So what I'm claiming is, if I looked at the polynomial, well, let's look at the polynomial b, which is let's define the polynomial. Let's look at the polynomial b of x, which is defined to be just a of x minus 1. The degree is preserved by this process. And let's look at just the evaluation of b of x. What is the evaluation of b of x? P of 0 is b of p minus 1. So b0, b1, p minus 1 is exactly in fact equal to, it will be what, ap minus 1, a0, all the way up to ap minus 2. So the Reed-Solomon code is a cyclic code. We never define cyclic code, but cyclic code with just which there's an ordering among the coordinates, and cyclic the code is preserved under cyclic code. So this, you will see that cyclic codes are nice for certain reasons. And one of the reasons for working in set of evaluation, yes. So and the field is a prime field is the corresponding Reed-Solomon code. All the Reed-Solomon code with the evaluation points are the finite field. Yes, the entire finite field FP, the code is cyclic. Okay. By the way, this is not true if it's not a prime field. Because you want a single element that will generate by addition. That's not true. That is because it's not a prime field. Once you add a number p times, it will just vanish. It will, you have to add another p to the r times for it to vanish. Because p times to it will just vanish. So the characteristic of the field is. But this is where we will use. So for prime, all I'm claiming right now is for prime fields with a set of evaluation points with the entire field, the Reed-Solomon code is cyclic. So it is creating in the fall of this R is cyclic. It has a nice form. Now let's look at what about non-prime fields. Not this nice part disappears in non-prime fields. So let's take Q. Where Q is p power R is not equal to 1. Here, what I say is true even for prime fields, but show that here we'll notice that the another property which fields that we have, that the multiplicative group is always cyclic for any field. This is a non-trivial fact. For prime fields, even the additive group is cyclic. That's what we have just seen right now. I want to say that multiplicative for every field, yes, every field, F2. So I want to say there exists for all Q from P per R, there exists omega in FQ star. So that FQ star is actually exactly 1 omega square all the way up to omega to the power Q minus 2. These are exactly the Q minus 1 elements. So the multiplicative subgroup of the field is always cyclic. Why is this? So now if you look at the evaluation point, S is equal to FQ star. And let's I'm going to write P of 1, P of omega, all the way up to P of omega to the Q minus. I shouldn't use speed, but use characteristic. gain. So that's a Rich-Solomon forward. Now, the same thing, if I take the Rich-Solomon forward, B, which is B of X, I define it to be A of omega X. Notice that this one, just like what we did, this is just going to cyclication. So S and Q star is a nice set of evaluation points because for every finite field, in fact, the original definition, historically, the definition of Rich-Solomon code was evaluation points was Q star because they were only concerned about cyclic codes, and this was how it came about. So when the old EE books, when they talk about Rich-Solomon, they talk about S being Q star, but they care about cyclic codes, and this is exactly the reason why. So cyclic code gives. What I want to say is B1 B omega to the Q minus 2 is exactly A omega to the Q minus 3. Sorry, Q minus 2 and A. Exactly this way, therefore RS is okay. 2 more minutes. Let's finish the parity check. So all of this is fine. So this is one of the right reasons. So one of the reasons for working with XQ star, people are interested in cyclic code historically a lot. And Rich-Solomon code is a cyclic. When they say Rich-Solomon code is cyclic code, they refer to this particular choice of evaluation. It's not true at all other evaluations. I could choose another set of evaluation points for which I don't have a cyclic. But the usual, when they say Rich-Solomon cyclic code, we usually refer to the evaluation point being excused. Parity check. So now let's look at one more. Parity check representation. For instance. So here, well, the generator matrix representation, we gave it for any set of eval, we gave it for all this one. Here, what I will do in class is only when yes is the entire field. The evaluation points. Yes, the whole field. For other Rich-Solomon codes, it's usually not there, but I will push this. I will go on the second problem. Let's see what is this. We need a basic information, and that's where I needed the multiplicative generator for this one. So let's want to look at summation. We're going to study this simple one. We're going to look at consider summation alpha power I, where alpha is in the field and I is some number between 0 and Q minus. Notice it doesn't ever make sense to go larger than Q because then I can come back to only look at these experiments. I want to look at what's the sum look like. So let's look at some basic cases first. Let's start off with I equals 0. I equals 0, this is defined to be alpha to the power 0 is defined to be 1. So what is it in that case? Summation 1 alpha and f. What will this be? Mod f, but what is mod f? Q, what is Q in the field? It's 0. Okay, so this is 0. The sum is 0. What about then I is Q minus 1? No, same thing. This is the same thing. So alpha power Q minus 1, what is it? In the field, it's equal to 1 if alpha is not 0. If alpha is 0, it is 0. Therefore, this is the 0 case goes out as separate, and then you say alpha in FQ star 1. So then what's the sum going to be? -1. This is still Q minus 1, so it's -1. Okay. Let's now look at the more general case. Now let's look at when 0 is less than I, all the other cases. Summation alpha to the power I. I want to look at the sum. So we want to write this is, let's take out the 0 part, because that's all we're going to compute 0, and that's why I took the I equals 0 case, because 0 per 0 is 1. So that I handle that case separately. But here the 0 case, the alpha being equal to 0 just contribute 0 to this. So this is the same as alpha in F star alpha per I, and here I'm looking since I is not equal to 0. Now F star has a nice form that is every element in F star is of the form omega per j for some j. So I can rewrite the sum in the following way. I can write it as, instead of writing with alpha, I can write j going from 0 to q minus 2 omega per j the whole power. Now, with the order of this one, this is omega per ij. This is the geometric progression. We know how to do it. What will it be? 1 plus a plus a square all the way up to a power r minus 1. What is it? It's a power r minus 1 by a minus 1. So what is? So first we have to check that the denominator is not 0. What is the denominator? The denominator is omega power I minus 1. And that is not 0 because I is not 0 or not q minus 2. We have taken off those two. So this I can write it down because I doesn't belong to 0 or q minus 1. The numerator is omega per I. How many terms are there? Q minus 1 term minus 1. But what is this? Once again, swap the things. It's omega per q minus 1. What is that? 1. Omega per q minus 1 is 1. So 1 minus 1 is 0. So this thing eventually happens to 0. Okay. These are some basic Fourier stuff, but I want to say at the end of this, what is the main proposition that we have? The following summation alpha per I alpha in F is 0 if I is less than q minus 1, and it is minus 1 I equals q minus 1. So that's fine. That's the summary of it. So it's always 0 for every I except when